And so in this case, the Lagrangian would just, for example, be 1/2 m r dot squared. Well, let's work out the, we'll do it in polar coordinates just to be weird. How about that? There's my Lagrangian in terms of the polar coordinates of one free particle in 2 dimensions. Or the Lagrange equations, simply this, partial L, partial R. And it's nice to start writing them as like this form. See, I just moved it to the other side to give an equality rather than setting it equal to 0. Do you see? It's the same as I had before, but you know, before I was writing it this minus that equal to 0. Now let's just write it this way. So that you have the one Euler Lagrange equation for your one dependent variable, namely the radial coordinate, but you also have an Euler Lagrange equation for your other dependent variable, which our current choice of coordinates would be the radial, the angular coordinate. All right? And so what do these look like? So what's this equation give us? Partial L, partial R is what? Is there an R dependence? Well, there sure is right here, right? So that gives me the 2's cancel. We just get m r theta dot, right? And that's ddt of partial L partial R dot, which is what? That's just mr dot, right? So what does this tell me? Apparently, we have the situation that mr theta dot must be equal to mr double dot. Okay. So there's my one Euler Lagrange equation. Not, unless I'm missing something, that's not terribly enlightening, but there it is. Now this one down here maybe will be proved to be more interesting. In fact, maybe after we solve the next one and we look at the first one, it'll start to mean more to us, okay? Like, what is partial L partial theta? Is there any theta dependence here at all?
No.
Nope, so that's 0. And then we've got ddt. What's partial L partial theta dot? Well, it's, oh, look at that, it's just 1/2. Oh, my bad. I'm so sorry, Ernesto. I have messed this up. It's not just theta dot. That is theta dot squared. Oh, yay, you can. You'll have to open it. Cool. I don't know why we get locked in here. Here, I'll get you started. Do, 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 do.
Horizontal line, we get 2 as
Mm-hmm. All right.
okay, good thing.
All right, I'm back. So that was supposed to be a theta dot squared in the speed, of course, because, well, if you work it out, that's what it is. I actually had this as a problem in my Calc 3, actually. You can derive this formula from just like differentiating the polar coordinate formulas. If you differentiate, you know, if you just differentiate x equals to r cos theta, and you differentiate y is equal to r sine theta, with the understanding that x and y and r and theta are all functions of time, then you can relate the rates of change. And when you calculate x dot squared plus y dot squared, you end up with an r dot squared term multiplied by sine squared plus cosine squared. And you end up with a theta dot squared term, again multiplied by sine squared plus cosine squared, but there's also an r squared in front of it. And then the cross terms end up canceling. You get a plus 2 and a minus 2, and you just end up with this. Now that puts a 2 here, which puts a, let's see here, this one, right? Because that was partial L, partial R, the 2R, m over 2, give me mr like that. And yeah, okay, so then partial L, partial theta dot gives me what? Actually, m r squared theta dot. Oh, this one? Yes, thank you. Okay, cool. So then what? Ah, well this is the one I just wrote in red is super valuable because that says that this quantity, whatever it is a constant, right? In fact, we have a name for this. You might recognize it in physics as I omega. This is L. The moment of inertia for a particle of mass m about the origin is mr squared. Theta dot is omega in the usual physics course. So that's angular momentum times angular velocity. Excuse me, that's the moment of inertia times angular velocity. This is exactly the statement that angular momentum is conserved for a free particle. And in view of this, of course, you've got L is equal to m r squared theta dot, right? So you can solve that for theta dot equals to L over mr squared, right? And you can plug that back up into here, and you'll get m r L squared over mr squared is equal to m r double dot which gives you what? Oh, make sure I didn't make another mistake. Man, this is so much easier for Cartesian coordinates. Interesting. I bet this is a homework problem. Now, when I square theta dot, do I just get L squared over mr squared? I do not. What do I get? I get mr squared squared, right? Right? All right. And then I get a, let's see here, to keep me honest here, we get L squared over mr cubed is equal to, you know, r double dot. Interesting.
Then you have an m squared in the bottom.
But oh yes I do. Thank you. I'm suspicious. Okay, then the question is, can you solve that? You know? So this would be something like, you know, like the r velocity dt, right? And well, I better stop there. I'm not sure what I'm doing past this point. So I just say, well, we found that, okay? Now look at how much easier this is. Look at how much easier this is in Cartesian coordinates, right? So in Cartesian coordinates, we just have 1/2 m x dot squared plus y dot squared, right? What are the Euler Lagrange equations? You got like partial L, partial x is d dt, partial L, partial x dot, and partial L, partial y, d dt, a partial L, partial y dot. But what are those? What do you got here? You got 0. Partial L, partial x dot is just mx dot. So we've got mx double dot. And this becomes 0 is equal to my double dot. Which, of course, are Newton's equations for a particle in free space without any force on it, right? It's just ma equals to 0. The thing is, ma equals to 0, what that means for polar coordinates, it's actually kind of complicated. You know? I mean, I guess it might be interesting to look at some, man, goodness, that's really troublesome to me. If I have, sorry, I'm thinking about things. If I have the r velocity is 0, whew. I'm just thinking about what if I have r double dot equal to 0? I feel like I'm missing something here. So anyway, I think that's probably a good place for us to stop today. I think I probably owe you like another hour of calculation in this stuff, right? I mean, I haven't quite finished things today, so we'll come back after break and we'll look at a few more problems and hopefully they'll make more sense. I don't think this is wrong or anything. Oh, well, one more example. Here's a nice one. Suppose you want to find like the geodesic on a cylinder, right? So you want to find the point that goes from here to here, which is, you know, like the path of the closest, you know, the length minimizing path. So on a cylinder, of course, the arc length you can write as, well, we can always write it as like dx squared plus dy squared plus dz squared, you know, square root, something like that. But if we want to think about this parametrically, which we really do, we can look at that. Okay, so that's really x dot squared plus y dot squared plus z dot squared dt, right? And okay, so surely if I minimize the square of that, that would also be, you know, length minimizing. So maybe I should just look at my my action here of x, y, z equal to like integral of x dot squared. Okay, but more to the point, sorry. This cylinder, right, is what? It's x squared plus y squared equals to r squared, right? So it would be smarter for me to trade this for like a r dot squared plus, all right, so like, my bad. So this is r squared, right? Like the cylindrical coordinate. So if I look at the speed, I guess I can afford a square root. Fine, I'm gonna regret it. If I look at the speed in cylindrical coordinates, I get this stuff again, right? But if r is constant, little r is constant, then this piece drops out, and that just becomes. And I'm just talking about speed squared here for a second. So that's r squared theta dot squared, right? plus z dot squared. So if I minimize that, that is literally the arc length formula for a path on the cylinder. All right, so this is my Lagrangian. So in this case, I want partial L, partial z to be ddt of partial L partial z dot. And I want partial L partial theta to be ddt of partial L partial theta dot. Okay? Now, there is no z dependence, and there is no z dependence manifestly in L. So the left-hand side is 0. So we get 0 is equal to, 1 over 2L, right? It's 1 over 2L. And then the derivative of the inside with respect to z dot is what? 2z dot, right? And on the other hand, we have 0 is equal to 1 over 2L times what? 2r squared theta dot, right? But I'm supposed to do what? dd, if you don't mind, I'm sorry, Ernesto, it's just so much easier. I should really talk about this more, but let me just erase that square root. I'm so sorry. If you forgive me. Erasing the square root makes my life so much easier, because then I just have this. And of course, we're differentiating that, right? So how do you solve those? Well, we have z double dot is equal to 0, and we've got theta double dot is equal to 0. The solutions to those are simply z is equal to z1 plus tz2, and theta is equal to theta 1 plus t theta 2. It's linear in z, it's linear in theta. Then you might wonder, okay, well, how to understand that solution? Like how to understand that solution? Well, if you like, I could write the formula for it more explicitly. It's, you've got x is equal to r times the cosine of theta 1 plus t theta 2, yeah? Y is equal to r times the sine of theta 1 plus t theta 2. And of course, z is just equal to, z1 plus tz2. Now, I don't know if it's totally obvious in the current system, but if I had a piece of paper, like this one, for example, and I just, took 2 points on the paper, and I just connect those by a line, all right? Then if I'd set this problem up more carefully, we could have asked on this cylinder, what's the geodesic, the path of least distance between the 2 points? And that line that's been curled like that, that's exactly what these are. It's just, if you were to take the cylinder, lay it flat, and then just curl it, it's exactly what that is. So I don't know if it's entirely obvious from my current approach, but anyway, I seem to have made a mess of that. Anyway, I'll try to do some less frantic work after the break. So thanks, guys. Thanks, everybody.